Welcome to Unit 4 of Programming 2 Pointers. In this unit, we are going to cover the introduction and the definition of pointers. We are going to look at the variable in relation to the pointers. We'll look at the differences between a stack and heap memory, what is referencing and referencing in relation to pointers, declaring pointers and assigning values to a pointer, the arithmetic operations on pointers. We are going to be able to create a pointer of a pointer, and we'll look at how we can work with the arrays of pointers. We'll look at the functions and pointers, how we can send maybe a pointer to a function, and probably how we can return a pointer from a function. Then we'll look at dynamic memory allocation, and the two more concepts there that will be covered under dynamic memory allocations will be memory leaks as well as dangling pointers. Let's begin our journey. To this far, we've been working with the variables, and those variables been working with, we've been interested in the value that we put the variable and the variable name. When we have declared a variable where we are able to assign some value, and we are able to get that value using a variable name. But there is one thing that we've not been paying attention to. Of course, we know that when you have declared a variable, that variable is allocated some space in memory. And we don't know which part of memory is this variable allocated. We're just interested in the name of a variable that we'll use in our program, as well as the value that we have assigned on that variable. But in this unit, we have an interest on the memory, where that variable is located, the location, the address of that variable. So a pointer is a special variable whose value is the address of another variable. So when we have a variable, we can use a pointer to get the address or to keep the address of that variable. If we declare a variable, maybe integer, maybe we say a variable of data type integer, and we say this is a maybe age. This variable is created in memory, and we can use a special variable to get the address of this, or we can use the address, we can point the address of this. So instead of using the name, we can also use the address to manipulate the value for this one. Instead of using a name to assign, we can use the address to assign a value. We can use the address to read the value for this one. So it's a special kind of a variable which can contain a memory address. So when we are looking at a pointer, we are looking at a variable whose value is never 2, 3, 4 whatsoever, but a memory address. The variables that we've been working with have been storing some value. It can be maybe an integer, double, or maybe a value of a string, maybe a name, or maybe whatsoever, a boolean. These are values we've been keeping. But here we are saying, instead of keeping that, we can declare a variable which cannot accept a name, cannot accept a number. It can only accept the address. That variable is called a pointer, because it just helps us to point to where the variable is located in the memory. It just gives us the direction, the address, that this one is found on this address. If somebody is to follow that address, it's going to find the value there. So we have here an example of how we've been declaring our variables. So we have declared a variable num. So here the num is the name of the variable, which we call identifier, and this variable is of type integer, and it, of course, it has been given a value 25. At this stage, we really don't know where exactly in memory num has been allocated. We don't know the address of num. There's a way for us to know the memory of a variable in C or C++. We can get the memory of the variable by using the ampersand. Like in this case, we have for the previous declaration and assignment statement where we have num equals 25, then here we can have cout statement. If of course we just say cout statement num, it will display the value which is 25. But if we have something like cout, then ampersand num, this one is going to give us the address of num. So instead of displaying 25, it's going to display something like this, which is an address of num. So we say variable num has address of blah 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 blah. Of course, if you try this one on your computer, you may not get exactly this. This is just a sample of how the address will appear like, because it will give you the address of the memory in your computer, so it might be different. Before we explore how we can declare and access values in of a pointer, how we can declare a pointer, access a value using a pointer, etc., we want to understand the concept of stack and heap memory. Applications that we create in C++ use memory in different ways, or divide the memory in two categories. We have the first part of memory which we call stack, and another part of memory which is called heap. You can use any of these memories, but just to maybe speak generally, the stack memory does not require programmer to manage it. You can allocate something on a stack memory as we have been declaring. What we have been using so far is a stack memory, and we are not responsible for deleting that memory or declaring that memory that we no longer need to use it. As we're going to see later, this second type of memory, which we call heap, the programmer is responsible. It's not just declaration or the allocation of memory, but after you have finished using that memory, you need to tell the program that I'm done. So you deallocate. So all the variables declared inside the current function will take up memory in the stack frame. So this is what we've been doing. If we have declared any variable, that variable is in the stack frame, and it will take some memory in that stack frame. If a current function calls another function, a new frame is created. So there will be a frame for each chain of calls. If one function calls another, then we have one frame here and another frame there. Each frame will be managing or be having information about that function. The variables for that function that have been declared will be managed on that frame, and these frames are actually placed in a stack data type. So the frame for the first function will be the first one to be placed in a stack, and if this function calls another function, it is going to create another frame, and all the details for that particular function in terms of variables declared etc. will be placed on top of this old frame. And if this calls another, then that third one will also be placed on this one. So if we are done executing maybe the third one, what it means is if we had 3 frames, if we just have them as stacks, if we are done with the third one, then this is going to be destroyed from the stack. And all the variables that were declared within it are destroyed also. This is a concept that we saw when we were looking at functions, that the variables that we declare within a function are local to that function. If we finish executing that statement, that function, or maybe we have a return statement, all the variables are destroyed. This is how a stack works. So as a programmer, you don't need to explicitly deallocate values from the stack, because the moment they are done executing that particular function, all the memory allocated for variables within that frame is released. So here we are just showing you some maybe frames, just a depiction of a stack frame. We have the first one, which is for the main, and we have created another one which is for a function called for, and it has got 2 variables, I and j, with values 7 and 11. So this for is on top of main. After executing for and everything is done, the control is going to be returned to the main function, and this frame is going to be destroyed. By destroying this frame, it means even the variables that were declared within that particular function, a function of 4, which is I and j in our case, will be destroyed as well. So as we can see, the frames helps us to the frame will help us to these frames will help us to have isolated memory workspaces for each function, because there will be a frame for each function. So if we are making any call, that function has got its own space. If a variable is declared inside one function, listen, inside one function's stack memory, calling another function will not actually change it unless we specifically tells it to do so, as we've been doing before. We've been able to do so. So if you specifically tells it, if you specifically tell it that here we want this variable declared in this function to be modified in that other function, then you can do so by maybe calling that other function with the reference parameters or reference arguments. But in our case, we are generally just making a statement here to say, if you have declared variables in one function and you call another function, that other function cannot see the values of this other one because they are in 2 different frames. Okay, so we have already stated about this. And on the other hand, the heap is an area of memory, which of course in most cases the heap memory is larger, bigger than the stack memory. But this is an area of memory that is completely independent of a current function of stack frame. And the heap memory, there is no order as in a stack memory. The heap memory things are just scattered as things on a heap. So there is no order, and that's why the programmers are supposed to manage the allocation of memories from a heap. So variables on the heap may still exist. This is something. If you have allocated something on a heap, it may still exist even when the function which this variable were created in actually have or has completed executing. So as we discussed before, we are saying for a stack memory, all the variables that were maybe declared within that for a stack memory, all the variables that have been declared within a function, the moment the function stops executing or finishes executing, all the variables are destroyed. In other words, the memories which were used for that function are released. But if you allocated some variables in that function and those variables were allocated on the heap memory, even when you are done or the function has finished executing, the heap memory that was allocated will still be existing if you forgot to delete it. So that's why it's a responsibility of a programmer to manually delete or deallocate that memory that was created. We are going to see how these are actually done in the later part of our unit. Yes, so here we're just trying to tell you that maybe just for you to appreciate that what we have been doing so far, or what we have been working on in terms of memories so far, are actually memories on the stack. If you are to use a memory on the heap in C++, you use the new operator. To this point, we have not been using a new operator. So we are going to see how this is done, as I previously said, towards the end of our unit. The good part of the unit is going to be on the on the stack memory, how we can declare pointers on the stack, etc. But later we are going to be working on the dynamic memory allocation that requires to have the heap memory. So the dynamic memory allocation is allocated on the heap and it must be deallocated by the programmer, while on the stack the programmer is free. You don't have anything to do with that. The program will actually manage on your behalf. Okay, so we can stop here in this video. In the next video, we are going to look at how we can declare a variable of type, a variable which is called a pointer, and how we can assign a value to that, and how we can access values using a pointer, and many other concepts related to that. Thank you.